Same inference request. Same input. Same API, same model name. One region returns allow, another returns review. You open your dashboards. CPU is normal. GPU utilization is normal. Error rate is near zero. Even your global P99 is technically inside the SLO. Everything is green. And yet, your system is returning different answers depending on where the request is executed. The cause could be a queue delay of just 50 milliseconds. Not because 50 milliseconds changes the model, because it changes the execution path that produces the answer. Let me separate this from classical model drift. The weights did not mutate while the request crossed the Atlantic. What we are investigating is operational inference drift. The same logical request producing region-dependent behavior because different execution paths were selected. That can happen when latency causes the system to miss an ensemble deadline. Switch to a smaller fallback model, read from a stale feature store. Use an older retrieval index or lose session affinity. Physical distance establishes a latency floor, but distance alone does not create buffer bloat. Congestion, queue growth, and overloaded gateways create the unpredictable tail. And it is usually the tail, not the average, that crosses a deadline and changes system behavior. Here is where OpenTelemetry becomes useful. Treat the trace as the spine of the complete inference request. Use child spans for operations with meaningful duration. Edgeroute gateway queue context fet, model prefill model decode ensemble branch result merge. Then use span events for decisions. Route selected, deadline exceeded, branch excluded, fallback activated, output committed. Your resource attribute establish the execution context. Cloud region model version request, deadline ms cache.hit. The events explain the decisions. Queue waiting is a duration, so it deserves a span. A fallback being activated is a moment, so it is a span event. Notice what we are not doing. We are not putting full prompts or raw model responses into trace attributes. Use controlled decision classes and safe fingerprints. Build 3 connected views. View 1, the geographic route matrix. Place source region on one axis and destination on the other. Show P50, P95, P99 for every route pair. A global P99 can hide one unhealthy path. The route matrix cannot. View 2, the correctness overlay. Display deadline miss rate, fallback activation rate, branch exclusion rate, and output disagreement rate. Now you can ask, when this route becomes slow, does the system merely respond later, or does it begin making different decisions? View 3, normal and divergent traces side by side. The normal trace completes at 215 milliseconds. The affected trace completes at 265 milliseconds. Then the event sequence reveals the real incident. Deadline exceeded, branch excluded, fallback activated, output committed. Once you can observe the causal chain, you can begin controlling it. Do not trigger a circuit breaker because of one unusual trace. Build the control loop in stages. Establish regional baselines per route pair. Combine performance and correctness signals. Tail latency plus deadline miss, rate plus fallback activations. Add guardrails, minimum sample sizes, rolling windows, hysteresis, cooldown periods. Make rerouting correctness aware. The nearest region is not automatically the safest. Before shifting traffic, validate model compatibility, feature freshness, and session affinity. Preserve the evidence with tail, sampling on deadline-exceeded events, and fallback activations. Multi-region inference does not fail only when a region goes offline. Sometimes every region is available, every container is healthy. Every API returns 200, and the global system still violates its consistency contract. Your traces should not merely tell you where the request spent time. They should tell you which decisions that time caused. Here is the challenge. Take one production inference request and trace it from route selected all the way to output committed. If the routing, ML platform, and observability pieces are owned by different teams, share this video with them and run the exercise together. Where does your system make a silent decision when a deadline is crossed? The router, the retriever, the model, or the ensemble? Drop your answer in the comments. Subscribe for the next deep dive.